So when designing hardware, traditionally, if you want to design a new chip, you'll want to have the most control over the logic that eventually gets, of the logic of the actual chip that you want to design. And so you might write it in a language like System Verilog, which is shown below, where you give a bunch of, you state exactly which components you place where and how they're connected. However, often there are parts of your hardware that you might not, that might have a larger design space. So you want to start exploring various different designs of this specific piece of hardware, or it might be quite a simple pipeline of arithmetic operations where you just want to optimize it as much as possible, but doing so manually would be quite painful. And so for this, there are high-level synthesis tools which essentially take C code and translate that to hardware. So this has various different advantages. So first of all, you can do testing at the C level instead of at the hardware level. So you can just run the C code on the CPU. And this is much faster than actually simulating the hardware at a cycle accurate level. And you can also design. You can give the high-level synthesis tool various different parameters, and it will spit out different hardware based on this. And so you can experiment with different architectures. So ideally, this speeds up verification and design at the same time. However, it's known in the hardware community that these high-level synthesis tools are unfortunately quite unreliable. So to test this, we also fuzzed them a bit with CSmith, and we found bugs in all the tools we tested. Some of them aren't listed here. So here we have a diagram where we essentially find the number of test cases that failed in each of the tools. And so traditionally, when you're using HLS, as Alistair actually showed, you will generate hardware from your high-level description, and then use an equivalence checker to check that the high-level synthesis tool didn't introduce any bugs in the design. But as Alistair mentioned, the equivalence checking tools themselves can be buggy. Hopefully it doesn't line up with bugs that are actually in the HLS tool, so it's still fairly reliable, but that could happen as well. The main problem is that this equivalence checking is very expensive. And so for every single translation that you do, you have to redo this whole big equivalence checking. And the larger your design gets, the more expensive this gets. And at some point, it doesn't scale anymore. One surprising additional point, which was another motivation for this work, is that HLS tools actually have custom C++ semantics, which is great. So, for example, there are a few bug reports saying like, oh, if you have a pointer to a pointer, you get this weird result. It doesn't result in any warnings, any errors, nothing. You get a very strange result when dereferencing this particular object. And the answer to this as well, on page 903 of our manual, we state that this is explicitly not supported, so you shouldn't have been doing this in the first place. And these tools differ in what parts of C++ they support, and usually it's not. They won't explicitly error out when they don't support a construct. So we wanted to build a more robust HLS tool that doesn't have this problem. So first, it solves we want to solve the reliability issue, so you don't have to do this formal equivalence checking. And second of all, we want to have quite a precise description of what input we actually support. And so we want to support C as input. And so we decided to reuse the ComCert compiler, which is a very successful verified compiler written in Coq or Rock. And it has a C semantics and various different assembly semantics. And it verifies translation passes to go from C to assembly in the Rock theorem prover. And so the whole compiler is written in Rock. And so we decided we also wanted to use like a tool you could actually use in practice. So we didn't want to create our own random C semantics, and we also didn't want to create our own custom C front end. It's quite complicated, and so we wanted to build upon ComCert, and so we build a custom hardware backend essentially, which is also written and verified in Rock. And so the first version of this was extremely simple. We just first came up with, we borrowed some Verilog semantics, tweaked them a bit to make them usable for a high-level synthesis tool, and then built very sequential hardware from the C code. And so it essentially executes like a processor, each instruction every cycle. So this isn't really usable in practice. And so we then spent a lot of time implementing a state-of-the-art scheduling algorithm, which is kind of the core reason you would want to use an HLS tool, is to automatically reorder instructions and place them into cycles so that you minimize some kind of resource, if that's latency or resource usage of area of the hardware. So I won't be talking about all the new passes we implement. Instead, I'll just be focusing on scheduling and kind of describe how we what it does, and how we then verify it. And so at the core of it, scheduling is essentially reordering instructions to minimize some kind of resource, so latency or area, and using various different heuristics. And in this case, for example, we have 3 instructions, and on the left-hand side, there are a bunch of dependencies between the instructions. And so, in this case, so we have predicates, and then these are predicated instructions. So they only execute if the predicate is actually true, if value is true. And in this case, there are a bunch of dependencies, so it would have to be executed sequentially, one every cycle. And so the scheduler should reorder these instructions so that so that some dependencies aren't there anymore. And this can be because the predicates, for example, are mutually exclusive, so you know that they can actually be executed in parallel, and it was a false dependency. And so you would get a cycle where now you have 2 instructions executed in parallel instead of them being placed into 3 separate cycles. And so the scheduling algorithm is quite, it's based on a ton of heuristics, on some models of the final hardware that we're targeting. And so we don't really want to verify the scheduling algorithm itself. Instead, we want to build a validator, and we verify this validator in Rock. And so in this case, we can symbolically execute both sides. We get some kind of symbolic representation of each value associated with each register, and we make sure that they're equivalent. One problem is that we use, we have predicated instructions, because in an HLS tool, you kind of have the advantage that you're not targeting some kind of CPU architecture. You can kind of come up with your own CPU architecture. And in our case, we just come up with an architecture where any instruction can be predicated, because that's totally fine from the hardware point of view, and it gives you quite efficient hardware where you can now schedule many more instructions in parallel. But the problem is that to check that some transformations were correct, we have to use an SMT solver. And I think a lot of times you can trust an SMT solver and you'd be happy to trust it. But in this case, we didn't really want to increase the trusted code base. So we just want to trust Rock, the theorem prover we're writing in. And so one contribution of this work was to integrate an SMTCock, the verifier written by SMTCock, for SMT certificates into the verification, into the validator. And so we have a validator for the schedule, and then we have a validator on top of that for the SAT queries emitted by our validator. And it's all, verified. So in conclusion, we built VeriCert, which is a formally verified and now optimizing HLS tool. And so the verified, the scheduled version of VeriCert achieves a 2x speed up on the original one, which is quite nice. But we're especially we're quite happy because we managed to at least compare against existing optimizing HLS tools. So we're still slower if you really add all optimizations, including all LLVM optimizations to existing optimizing HLS tools. But from the scheduling point of view, we're not doing too badly. So there are a bunch of more optimizations we'd love to implement. So this is these would be great to have. So to catch up to existing HLS tools, especially loop pipelining is one that is quite important if you want efficient schedules on loops. But what I'm especially interested in are these two last points. So now that we have VeRSert, we'd love to be able to actually use the proof that the end-to-end proof that we have. And so we'd love to use maybe existing proofs of programs that were verified using VST, which is the Verified Software Truth Chain, which is a framework used to verify specifications on CompCert C code. So we'd love to use that to actually show that you can transfer these specifications onto your hardware and you get the same properties on the hardware. And finally, what I'm working on now in my postdoc is trying to extend VeRSert also to tackle data flow architectures. So this is becoming increasingly popular when you really care about latency and not too much about hardware. You can create these data flow graphs, or especially with ML, I guess it's getting even more popular, where you have nodes that are connected in a latency-insensitive manner, and they will dynamically schedule themselves to get the fastest throughput. So thank you. I'd love to thank I'd love to thank VETS for all the support. Without that, this research wouldn't have happened. And I have fond memories from my first conference, which was also a VETS conference in 2019. So before I even started the PhD, so that was great and enjoyed all the discussions. Thank you.
Thank you so much, Yann. I should also mention that, as Yann said, he's a postdoc these days at EPFL, so we're very grateful for him to travel internationally and make time to be here with us today. So thanks again. And also, as Simon said, as VETS, we care about impact, of course, impact within this room, but more importantly, as you mentioned, impact outside of this room. And I think we can all agree that all three award winners exemplified this with their research. So well done, congratulations, and thank you.